This is lesson number 2. We're going to look at equations and expressions today, kind of highlighting the similarities and the difference between them. And on the left, I've got a nice expression that's sitting there. It doesn't have an equal sign, so it's not an equation. And then over here on the right-hand side, this is definitely an equation because we've got that beautiful equal sign sitting in there. We're just going to talk about how these things are kind of similar and kind of different at the same time. Well, very different at the same time. And first thing I want to talk about are, what are the verbs? What are the actions that we can do to these things? And for expressions, various instructions you might see. People might say, hey, let's go and simplify this expression. Or maybe the opposite. Maybe they're going to ask you to factor it. Or maybe we might be asked to evaluate it. Whereas over on the right, with an equation, the kind of one action, the one verb is to solve, right? To look for solutions. Okay, well, with each of those, let's kind of see how this would unravel. With the expression, maybe if I want to simplify it, I might want to distribute those brackets open, and then I could say, oh, that's going to be 1/6 x squared, and again, continuing to distribute, I'd have 3/6, well, that's just 1/2 x, and then plus 1/3. Okay, so there it is, still an expression, doesn't have any equal sign at all, just sitting there. And if I wanted to solve this equation, one of the first things I might want to do is clean it up a bit. I might want to distribute those brackets open and say, oh, okay, how about 1/2 x squared minus 3/2x is equal to -1. And if I'm going to continue to solve this, we'll see why on the bottom of this page, but I might want to have 0 on one side. So I'm going to just move things around here a little bit and say, how about we rewrite this equation as 1/2 x squared minus 3/2x plus 1 is equal to 0. Now I'm actually going to stay on this side of the page for just a minute and point out that on an equation, you absolutely can go and multiply both sides by a constant. That is an okay thing to do. And I might want to do that here to get rid of those fractions. So this is an acceptable thing to do, to multiply both sides by some sort of constant value. And in this case, as I look at those fractions, I can see the least common denominator is a 2. I might want to take the left-hand side, multiply it by 2, and maybe take the right-hand side and multiply it by 2. So just inserting my old equation in here, you can see I'm doubling up this 1/2 x squared minus 3/2x plus 1, and I'll double up on that 0 too. So I'm doing this to both sides. Seems like a perfectly fair thing to do. And when I do that, the fractions go away. It's quite nice. And I'm going to have x squared minus 3x plus a 2 is equal to double 0, well, that would just be a 0. Now, on that particular equation, I'm going to go and factor it, just to see what kind of factors I'm playing with. And this one looks like it factors x minus 1, x minus 2. Okay, and that's still equal to 0. And for an equation, if I want to solve it, I can actually solve it using something called the zero product rule. So you can solve equations with the zero product rule. All right, so let's talk about what that rule is all about. You've probably used this before, maybe not, but explicitly by name, but it's worth talking about. The rule is actually quite nice, quite simple too. And it says if you ever look at some math and you notice that you have one factor multiplied by another and it's equal to 0, if that's what you see, then there really is only one way this can happen. Then either A is equal to 0 or B is equal to 0. That's the only way you can get a product of 0. So that's why we rearrange everything and get the 0 on one side. Now I know we've been kind of leaning on this right-hand side of the page here, but let's finish this off, right? I can actually go and say, all right, up to the very top here now I have x minus 1, maybe that's equal to 0, right? These are my possibilities. So either for this equation, that first factor, x minus 1 equals 0, or the other one, x minus 2 is equal to 0. Then I just solve those independently. Of course, they solve pretty quickly. I've got x is equal to 1 or x is equal to 2. Now, those numbers that we found, we would say, hey, those are solutions, right, to the equation. There's another name that we sometimes use too. You could call them roots of the equation. So I've got some solutions, or you could say I've got some roots. Okay, now let's go back up and kind of take a look at how that would work for an expression. You know, what kind of stuff that you see on that side of the page can you apply over here? And the answer is not very much, because although you can multiply both sides of an equation by any constant if you wish, you know, to make it look nicer, you cannot do that with an expression. So I can't go and multiply by a constant. If I do, I change it. You know, I ruin it. So that's just not an option. It's not okay. It is not okay to say, you know what? I don't like this expression that's here, this 1/6 x squared minus 1/2 x plus 1/3. Yeah, it just doesn't impress me. Would it be okay if I just took the whole thing and multiplied everything by 6? I think it'll look nicer. And you know, it will look nicer, but you will have damaged it. You will have ruined it. You made it 6 times bigger than it should be, right? So sure, this looks pretty nice, but that's just not the same expression anymore. So that is off the table. We do not want to be doing that. So what are our options if you want to try to, you know, work with this expression and you happen to have fractions in there? You could do this. I'm going to say you can use a least common denominator to simplify. Okay, so what would that look like? I guess I'd have to use sixths, right? I could say, oh, well, that is like 1/6 x squared. And then where it had minus 1/2 x, I could go to a common denominator of sixths and say, hey, that's like 3/6 x. And then the 1/3, that's like having, you know, if I go with sixths down there for my denominator, that's like having a 2. So this would be plus 2/6. Okay, well, if I desire to, I could go now and factor out this 1/6. That's not changing the way this expression actually could get evaluated. It's perfectly fair. So then I would have this. And then, you know, if I wanted to, I could factor it. But that 1/6 still hangs around. It's part of this expression. So multiplying everything by 6 is not an option, but you could get a common denominator and kind of work with it from there. Now, one thing that you can do, another verb, another action that you can do with expressions is you can evaluate them. So we could pick, you know, whatever we want for x. We could even pick a couple of them. We could say, hey, can we try out x is equal to 2? Or maybe, whole new question, could we try out x is equal to 3? And just watch what happens when we evaluate this expression. I don't need to put in an equal sign anywhere. I'm just going to rewrite this by now substituting in 2 for x and say, okay, that's 1/6 times 2 minus 1 times 2 minus 2. Okay, that would be 1/6 times a 1 times a 0. Okay, I actually get 0 when I evaluate for 2. Then when I try evaluating for x is equal to 3, I would have 1/6, 3 minus 1, and 3 minus 2. So I would have 1/6 times 2 times a 1. Okay, it looks like I get 1/3. Now, people might say this, just a little vocabulary you can throw at this. The fact that when we evaluated for 2 for x, and we received a value of 0, sometimes people will say this phrase. They'll say, oh, x equals 2 is a 0 for that expression. It's a number you can use for x and then receive a value of 0. So kind of looking at the whole picture here, let me just back up again. So expressions, we don't solve them. They're not equal to anything. We can simplify, factor, or evaluate them, but not by multiplying by a constant to get rid of fractions. You are stuck with those fractions. Whereas for equations, you don't have to tolerate looking at fractions. You can go ahead and multiply by a constant, you know, the least common denominator to clean them up. And then when you're ready, consider throwing everything over to one side and then applying the zero product rule in order to find what the solutions or what the roots are. Okay, so let's look at our next page here. So on this page, we've actually got some work with fractions, and we're going to go and look at the story over here on the left where there are just some numbers, and then we've got some algebra that's showing up in the fractions that are on the right. Well, let's do the little middle school fraction question first, see if we can come up with an answer there. And we're going to do this one by hand, okay, without our calculator, just trying to think about the plan. So I'm going to go and think about what that least common denominator would be, and to get there I might want to do like a prime factorization. You know, what do you have to multiply to make 54? Well, you could go 2 times 27, so 2 times 3 cubed, right? 27 is just 3 times 3 times 3. And then the 11 sitting on top of the 90. Okay, well, what's 90? Well, it's like 9 times 10, and a 10 is a 2 and a 5. So you'd have a 2, you'd have your 9, 3 squared, and you'd have a 5. And then you've just got this 1, right? Just a 1 sitting on top of a 1. Well, when you look at it with prime factorizations, you can start to think about what the least common denominator would be. It looks like I need to have at least a 2, and this one needs 2 3's, but that one needs 3 3's. So I need 3 3's, and we do need a 5. You need to have all of those things. Well, that's actually 270. That's the easiest, smallest number you can go to for a denominator in order to combine these fractions together. So here we go. That first fraction, the 7, sitting on top of the 2 times the 3 cubed. It's pretty good, but it doesn't have the 5, so we're going to have to bring in a 5, but it's got to be top and bottom, because I don't want to change the value of that fraction. So I'm not actually multiplying by 5, I'm multiplying by 1, right, if it's 5 over 5. Okay, looking at that next fraction, I'm going to write this as plus negative 11, sitting on top of 2 times 3 squared times 5. There's the 90. Okay, what's it missing? Well, it needs another 3, top and bottom. And then the 1, well, the 1 needs everything. It needs a full 270 kick in the top and a 270 kick in the bottom. Okay, now all the denominators are the same, so I have a chance of getting this to work. Looks like I have a 35 all on top of a 270. Got a negative 33 all on top of a 270, and a 270 all on top of a 270. So when we go to put these fractions together, we're going to leave the denominator the way it is. Okay, that'll be important when we go to do the algebra. And then we'll work with the numerators. So adding all those up, we're actually going to get 272. Now, you can tidy that up a little bit. You could say, hey, look, the top and the bottom both have a factor of 2 in there that could be extracted. So if we divide top and bottom by 2, that's fair. And we can say, hey, here's an answer, 136 all on top of 135. Great, well, that's middle school. But let's do the exact same thing now with some algebra and see if we can make the same thing happen. So we're supposed to put this expression together. It doesn't equal anything. There's no equal sign. So you can't just go and multiply by something to make the fractions go away. It's just not an option. But I could factor the bottoms, just like I factored the 54 and the 90 here, and say, hey, this is an x plus 4, all sitting on top of, okay, factoring that. I could do a GCF factoring here, 2 times x minus 2. And then minus, all right, what do we have? 2x plus 5. That's sitting on top of, this factors as x plus 1, x minus 2. And this is just going to sit here. I guess I could write that as 2 squared if you wanted to for the 4. So we got to think about what that least common denominator is going to be. What's the smallest amount of stuff that you can have that will work for our denominator? Well, it's going to have at least 2 2's multiplied together, right? It's going to have a 4 in there, and it needs an x plus 1, and it needs an x minus 2. So unless our denominators have all that stuff, we're not ready to go. We have to go and add stuff to the denominators to get there. For example, this first fraction, it's missing a 2 and an x plus 1. So that's the way it looked originally. I'm going to head up towards this least common denominator. But to get there, to get to that least common denominator, this one needs a kick with a 2, and an x plus 1. That was what was missing. Okay, continuing on. We've got minus this 2x plus 5. It's going to receive a kick as well as we make our way up to this least common denominator. That one's missing the 4, the 2 squared. And then the last fraction. Same least common denominator in here. That's what we're heading for. That's the plan. And that 3, that's going to get kicked with a fair bit of stuff here. A couple of binomials. An x plus 1 and an x minus 2. All right, let's clean those tops up so we can put them together. We're going to have, when we combine this thing, they'll all sit on top of one nice denominator. Right, that same old denominator. You can actually just do this in math to say, yeah, same old thing. Now, what's going to be up here? Well, multiplying this all out, this is going to be 2x squared plus 10x by the time you put all the x's together, because you'd have a 4x and another x to make 5x, and then a 2 to make 10x. So if you carefully simplify that numerator, you're going to have a 10x in there and an 8. Now this next part, be careful, the whole thing is led by this subtraction. So everything gets subtracted here. Both the 8x and the 20 get subtracted. And then finally this last term here, this last fraction, we can FOIL those together, then multiply by 3. We're going to have 3x squared minus 3x minus 6. Okay, so it's time to put all of those numerators together into one numerator, and we'll keep the same denominator on the bottom. So the bottom is just going to be, actually I probably don't need a fraction that big. It's starting to get simpler here now, so let's tidy this up. We're going to have in the bottom that same 4, x plus 1, x minus 2. And now what do we have? A 2x squared and a 3x squared. We have 5x squared. For x is 10 minus 8 minus 3, so minus an x. And then for the numbers, we've got 8 minus a 20 minus a 6. That's going to be minus 18. And we're getting close, but maybe we can make this a little bit simpler. Maybe there's some common factors there. So let's try factoring that numerator. The bottom is already factored, the denominator is factored. Yeah, you know what? Sometimes you have to factor these trinomials that don't have a 1 for their leading coefficient. And it's a bit of a hassle, but you got to come up with some plan for doing that. When you do, this one turns into 5x plus 9, then multiplied by x minus 2, all sitting on top of 4, x plus 1, x minus 2. Okay, well there's a common factor here that maybe we can reduce if we're careful and say, hey, you know what? Those two numbers are going to be the same. They won't affect the value of this fraction, of this expression, so maybe we don't have to write them. Hey, how about we just write this as 5x plus 9, all sitting on top of, now, leave it factored if you want, expand it back out, it's totally up to you, but I could write it like this. But it turns out that alone is not quite good enough. And you'll often, check the answer in the back of your math textbook and you'll be like, why did they say this? Why did they leave this note here? X cannot equal 2. And the reason is, when you reduce this common factor, you're now going to hide the issue that in the original question, if I go back up here, in the original question, putting in x equals 2 is a really bad idea. This expression has no meaning if you actually do that in the original question. So this answer we've got, this 5x plus 9 sitting on top of 4x plus 4, nobody can tell that 2 is a problem. So you have to leave the little note in there saying, hey, by the way, this thing, 5x plus 9, on top of this denominator, it'll give you the right value, but you should never assume it's okay to put 2 in, even though it looks like it's okay with that fraction down there. So for this fraction, it is fine, but with the original, it wasn't. So that's why that reminder is still left there. Just two quick little math reminders before we hit the next page. If you have negative exponents, that actually does not mean a negative number. It means that that factor is on the other side of a fraction bar. So this is actually 1 over 3 squared, right? It's going to be 1 over 9. If you've got a negative exponent here on this a, it does mean that that a is trying to get down underneath something, and it's going to get under the 3 only. It can't get past this plus sign. So this is 3 all on top of a, and then plus b. Be aware of the fact that it is not this, right? It's a common mistake. People will say, hey, can't I write that as 3 plus b, and then just put the a downstairs like that? That's wrong. That a cannot get under the b because of that plus sign. It kind of is a barrier to stop that factor from getting underneath the b. Another issue with exponents, if you have fractional exponents, that's another way of writing roots. So this would be a square root, right? We don't usually put the 2 in, but it would be a square root of 3. This one here, you could write this as a square root of a cubed, or if you want, totally the same thing, you can actually do the square root of a all cubed. It's exactly the same thing. So you do whichever is the easiest for you to calculate. All right, so on this next page here, let's talk about greatest common factor factoring. And we're going to add some ideas to that compared to what you've seen already in your math courses. So GCF factoring is probably the first factoring that you learn to do. People would say, oh yeah, it's the easiest one to do. You know, you look for a common factor, like here we've got a common factor of a in this binomial. We could extract it out. It's like distributing but backwards. And we could say, hey, that's a times b plus c. And that's great. And they were all nice, easy questions, you know, in Math 10. But now I want to show you a couple of unusual ways that you can do GCF factoring that are going to be really useful to us. This 18 x to the negative 1, that term right there is trying to say minus 18 all on top of an x. And I'm going to do something a little bit unusual looking, but it's really helpful. I'm going to look for a greatest common factor. Well, with the 12, the 42, and the 8, that would actually be a 6. That's fine. And now, what about the x's? Well, I might choose to try to get rid of this x to the negative 1. It might be kind of annoying me the way that it looks. So I might choose to extract an x to the negative 1, a 1 over x, essentially, out front. So what I'm writing here is the same thing as 6 on top of x. That's all that this is, right? So this GCF factor I've got out here is just a 6 on top of x. And now I have to think about, well, what's left inside this trinomial? This is really weird when you go to pull out a negative exponent. You have to think about what needs to go here. Well, what would you multiply by 6 to get 12? That's got to be a 2. But now for the x's, what number should I put here so that when I multiply it by 1 over x, I end up with x squared? Well, it actually needs to be x cubed. And the first time people see that, a lot of people don't like it so much. But if you think about it, yeah, 1 over x multiplied by an x cubed, that would actually be x squared. So I would have to have an x cubed here when it multiplies by this to get the x squared. Continuing on, extracting the 6, I get a 7. And then this would be x to the 6. So these x's are actually going up by 1. And then taking out the 18 and the 6, I'm going to have a minus 3. And I've taken out the x to the negative 1, so it just sits there like that. And you might look at it and go, well, why would you ever want to do that? It may be possible that now when I regroup this and put the x to the 6th first, I might say, hey, that kind of looks like a quadratic. Maybe I can do some more factoring to it. And it just gives you more options for factoring later. So it is something that we'll do, where we'll factor out unusual x factors just to make things look cleaner in what's left. This one here, remember again, x to the 1/2 is like a root of x. I might say, hey, this thing will look a lot nicer if I go and actually extract out an x to the 1/2. In other words, a root x. So what would be left? Well, remember, when you multiply terms that have the same base, you would be adding up the exponents. So you have to ask yourself, what number would you want to put here so that when you multiply these together and add these two numbers, you get 7/2? Well, if I want to add something with 1/2 to get 7/2, it would have to be 6/2, otherwise known as 3. Right? And then with this next term here, this would actually just be minus a 5. And so you could write this, if you want, as x to the 1/2 multiplied by x cubed, subtract 5. And maybe maybe you might have some factoring skills that work with this polynomial here that would let you keep going. So that's why we might want to extract out that root x out front. So we're always just thinking like, hey, well, what would you have to, multiply together by adding exponents to get back to the exponent that's there? We did it here. We also did it here as well. Just trying to get back to that number when you go to add the exponents up. Okay, just a neat little skill that we might use here in the next couple of pages. All right, still simplifying. Okay, we're going to do simplifying for this page and the next one until we get to some equations on the following page. This first one, it's not an equation. I can't just go and multiply by something to make the fractions go away, but I could look for common denominators. Right now I have a 2 on top of a 1 minus a 1 all on top of an x minus 1. Looks like the least common denominator is going to be x minus 1. So I have to head to that for my denominator. No problem. You can do a little multiplying here. This is going to be 2 times x minus 1 all on top of an x minus 1. There's your 2. And then subtract 1 all on top of x minus 1. Okay, putting fractions together, we're going to leave the denominator but work with the numerators. So we're going to have 2x minus a 2 and then subtract a 1, all sitting on top of this least common denominator of x minus 1. Tidying that up, about as far as I can get is 2x minus 3, all sitting on top of x minus 1. Notice just stylistically here, I'm working down the page and I have no equal signs anywhere. I'm not working across the page and writing equals, equals, equals. This is not an equation, it's just an expression that's sitting there and I'm choosing to rewrite it and rewrite it and rewrite it. All right, this next one on this page. Ooh, got this -1 exponent, and that's trying to tell you that this t plus 1 doesn't belong there. But it is not okay to take this t plus 1 and move it totally down to the bottom of this big fraction because of this plus sign right there. And the same thing with this plus sign, it's going to stop us from taking that t minus 1 and moving it up to the numerator. So we have to think about this in a different way. Let's look at it like this. We've got a big giant fraction. Put that over here. And it's got a 1. And then this -1 says, hey, t plus 1, you need to go underneath the fraction bar. Okay, so that would be like this. That is as far as that t plus 1 can get underneath anything. Down in the denominator, got a big giant 1, and then there's this 3, and then the t minus 1 will get underneath the 3 only. That's all it can get underneath. It can't get underneath that 1. And that is nasty looking, right? Some big complex fraction, a fraction of fractions. Well, there's a way out. We can take this giant numerator and this giant denominator, and it'll still be the same value expression if we multiply the top and the bottom by the exact same number. So I'm going to be fair. I don't want to change the value. I'm going to multiply this one by something and that one by something. Hopefully it'll clean it up. And I'm going to use the least common denominator of all of the little miniature denominators that I see. And here that would be a t plus 1 and a t minus 1. And I'm going to give this bottom gigantic denominator the same kick. I need to be fair about this. So this least common denominator is going to get kicked to this term and to that term. And the same thing down here. We're going to distribute to both terms. When we do, it's going to get messy looking, but it'll be better because it won't be a complex fraction anymore. It'll just be a big fraction. So when that hits the 1, yeah, okay, here maybe I'll keep them separate for a minute here. T plus 1, t minus 1, plus a 1. That 1 on top of t plus 1 gets kicked with this. The t plus 1 cancels, but not a t minus 1. All sitting on. Okay, here comes that big purple LCD, hits the 1. T plus 1, t minus 1. Still distributing, hitting this fraction with the 3. The t minus 1s will cancel, but not the t plus 1s. Well, at least it's not a fraction of fractions anymore. It's awful looking, but it's not as bad looking as it was before. Cleaning this up, looks like we're going to have t squared minus a 1 plus a t minus a 1, all sitting on top of t squared minus 1 plus 3t plus 3. Okay, can we make that any better? Yeah, we could write that as t squared plus t minus 2, all sitting on top of t squared plus 3t plus 2. I'm going to resist the urge to put in an equal sign and work across my page. Instead, I'm going to say, okay, look, let's just kind of wrap this around up to here, keep going. I could factor the numerator and the denominator here. That's t plus 2, t minus 1, all sitting on top of t plus 2, t plus 1. Oh, I've got a common factor that I don't need to have, as long as I realize that it is not okay to put in negative 2. And so I could tell people, if you don't want to evaluate the expression that the example started with, you just use this. This would be a much easier thing to evaluate. It'll give you the same answer. Oh, but by the way, don't ever put in negative 2. That would be bad. Right? So that little note does have to go there. On the next page here, we're going to look at another little technique, maybe in grade 10 you might have learned, for rationalizing expressions. And it turns out we can actually use this in calculus to solve some things called limits. So let's just go over what rationalizing is all about. It's probably when you might go and clean up any common, or I should say perfect squares that might be under a square root, but you might also find yourself going and multiplying the top of a fraction and the bottom by some sort of magical thing called the conjugate. Okay, so let's just do this by example. It's probably easier to look at and go, oh yeah, now I know what you mean. When we did that in grade 10. This root 20, you could think of that root 20 as being the same thing as the square root of 4 times 5, but 4 is 2 squared, and then the 5. So there's a 20 underneath the root sign. But when I have that perfect square, when I have that 4 in there, times the 5, I could actually extract it out. I could write this as root 4 times root 5, or in other words, just 2 root 5. And your Math 10 teacher probably told you, you have to write it that way. You're not allowed to write root 20. You have to write 2 root 5. Strange thing, the reason why we have simple radical form in that rule is so that people can use slide rulers when they're doing work with square roots. Well, we don't use slide rulers anymore, so it's not really a big deal to write down root 20. But it's still going to be a neat technique we can use to solve some calculus problems. This one here, this is the same thing as 3 sitting on top of this root 20 here. Again, that's like 2 times a 2 times a 5. It's not a perfect square, that 20, but really all it needs is a little kick with maybe a root 5. That would probably be good enough. I don't have to multiply by root 20. That's too much. If I just bring in a root 5, then I'll have these perfect squares. I'll have a 4 and a 25. Yeah, that will work great. And so the nicest way to write this is probably going to be 3 root 5 all on top of, okay, the 4 comes out as a 2, the 25 comes out as a 5, so I've got a 2 times a 5, so that's going to be a 10. Okay, so it doesn't have any roots in the bottom. Yeah, your Math 10 teacher probably told you you can never leave a root down in a denominator. Well, again, that's if you're working with a slide ruler. But it's still a handy technique, so let's practice this here a little bit. If somebody told me to rationalize the denominator, in other words, make it look nice, make it not have any root to it, not a problem. I could take this thing and multiply by root x, top and bottom. That's fair. I'm not making it any bigger or smaller. And I can make that denominator look nice. And I would end up with 4 root x in the top, so the top now looks nasty, but the bottom, a root x times a root x, well, that would just be an x. So yeah, I've made the bottom look nice. This one though is different because now I have this binomial down here in the bottom. I have two separate terms because of that plus sign right there. Here's where you really do need to use the conjugate. You would want to multiply top and bottom by something that's going to make the bottom look better. And if you just multiply by the bottom again, it doesn't work so well when you do the foiling. But if instead you were to multiply by that root and then change that sign that's creating the binomial to a negative, right? That's the conjugate. But if you're going to do that in the denominator, you have to do that in the numerator as well. So I'm going to multiply top and bottom by that. Okay. You know, in the top, I might just tell people that I would multiply it. I might not actually bother to do it. I might just leave this as 5x getting multiplied by root of x plus 2, take away a 3, and just leave it like that, especially in calculus. But the bottom, it's almost magical here when we see this difference of squares start to form. We've got the foiling creating a root x plus 2 hitting a root x plus 2, so that'll actually just be an honest full x plus 2. And then we're going to have the outsides and insides become opposites. We're going to have a 3 multiplied by the root and a negative 3, so they go away. And then the two 3's, they multiply together to make a 9, so we'll have minus a 9 down there in the bottom. So the bottom has been made nice, and the top's been turned into a mess. Tidying it up just a little bit more, I could write this as 5x multiplied onto the root of x plus 2, take away a 3, all sitting on top of x minus 7. So yeah, we've made the bottom look nice at the expense of making the top look awful. Let's try it the other way around. Let's try rationalizing the numerator. Probably something you never did in Math 10, but it could be useful for us in calculus. So if I was told to simplify that expression over there on the left, especially if they said, hey, make the top no longer an irrational number, I would probably go and say, hey, why don't we go and take this complex fraction, take that top there, and we'll multiply it by the least common denominator. How about by a root x? That'll work, as long as I do it to the bottom as well. So I have to multiply that also by a root x. Okay, when I do that, this root x is going to distribute. It's going to make that look really nice. This will turn into a root x. I'm going to have 1 minus root x. There's my top. And now down on the bottom, what's this going to look like? Well, how about I just leave it as some factors here for a moment. I'm just going to say that I'll have an x minus 1 multiplied by a root x. Okay, so I've gotten rid of the complex fraction, but I still have roots, both top and bottom. And they said rationalize the numerator, make the top look nice. Okay, sure, we can make the top look nice. How about we go and multiply this top by its conjugate? Let's go and multiply by 1 plus root x, because we were told, right, make the top look nice. Well, that should make the top look nice. But to be fair, you have to do exactly the same thing down here in the bottom. Okay, what happens when you do that? Well, we're going to get some foiling going on here. So 1 times 1 is 1. And then the outsides and insides are opposites. But then we'll have minus the root times the root. Well, that'll just be an x, so minus an x. There's my numerator. And what do we have down here in this denominator? Kind of a mess, actually. There's an x minus 1. There's a root x. And then there's this 1 plus root x. Well, we've done what they said. We've made the top look nice. It doesn't have any roots in it. We could make this a little bit better, though. We've got these two factors here that at first glance, they don't look the same, but they actually are. This factor here and that factor, they're just opposite factors. Okay, they're just reversed. It's really the same number. It's just that one of them is positive and one of them is negative. So we can actually take those out as long as we drop in a minus sign somewhere into the question. So I might say, hey, here's the best I can do. Here's my simplest answer. It does have no roots in the top. I've got my negative sign. There's my top. And then down on the bottom, I've got a root x and then a binomial. And a caution sign, a little sign that says, please don't put in x is equal to 1, right? X can't be 1. If you put 1 in, that'll cause some big problems. Even though it doesn't look like it here, it would cause big problems up there. Okay, last one, same game. If you want to make the top look nice, let's take this top, since it's a binomial because of that minus sign here, let's go and multiply by its conjugate, which would be the root of x plus 2 plus a root of x minus 5. Whatever sign you see here creating that binomial, we'll just take its opposite when we drop in this thing called the conjugate. If you're going to do that to the top, you better do the same thing to the bottom. Exactly the same number. We want to be fair. Okay, the foiling in the top. Again, it's almost magical here. The firsts, the two roots, that's going to create an x plus 2. And then the outsides and insides are the same number but opposites. They go away. Then we'll have a subtract because of this singular minus sign, and then the two roots of x minus 5. Okay, x minus 5. All sitting on top of this mess. Down here, I'm not even going to FOIL it all out. I want to kind of leave it as factors just in case something nice happens later. Okay, the top, I can tidy it up a bit. The x's will reduce. 2 subtract a negative 5, that's going to be a 7. And then the denominator, I'll just leave it the way it was. Nothing is going to factor and reduce here, so time to stop on this one. So we've made the top look nice at the expense of making the bottom look bad. Kind of the opposite of what you might have done in grade 10, but it still could be a really valuable skill for us to use in calculus. Now for our last 2 pages, we're going to switch gears. We're going to start to look at solving equations. So these are different, obviously, because we've got an equal sign in there, gives us some more freedoms, and it gives us a chance to do this solution finding where we can find out what the value for x is. All right, well, let's practice this deal here working with fractions. Looks to me like for this first story, the least common denominator of 3, 4, and 2 would be 12. You don't have to multiply all the numbers together and say, oh, 24, 12 is good enough. I'm going to multiply that term by a 12, that fraction by a 12, this term in the story by a 12, and that one by a 12. I'm going to make things 12 times bigger. And when I do, it gets really nice really fast. 12x divided by 3, well, that's just 4x. 12x divided by 4, that's just 3x. And then the other side of the equal sign, on the right-hand side, got my 7 times 12 divided by 2. You can reduce. 12 on top of 2 is a 6, times the 7 is a 42. Okay, tidying up a little bit. Looks like we've got 7x is equal to 42. Now, everybody kind of knows what happens next, right? We're going to say, oh yeah, you know, x is equal to 6, right? But really what's happening is we're multiplying both sides by the same number. We're saying, hey, why don't we go and multiply by 1/7 right now? Right? That's what's happening when you jump down to the next line and say, okay, x is equal to 6. There's my solution for this equation. There's my root. There's my value for x that's going to make the left-hand side equal the right-hand side. All right, next one. Ooh, a little more interesting here. It's got fractions and brackets. I would get rid of the brackets first by distributing. So this is going to be p squared on top of a 6. And then minus, again distributing. Going to have a p on top of a 2. And why don't we go and put everything onto one side? Let's subtract 2/3 from both sides. So minus 2/3 is equal to 0. If it's quadratic, that's usually a good plan. Okay, so you start looking at it and saying, all right, what's the least common denominator? Well, for 6 and 2 and 3, that would be a 6. Let's go and multiply every term here by a 6. Let's make everything 6 times bigger, including the 0, which of course will still be 0 when you make it 6 times bigger. Well, if you do that, all of a sudden the fractions are gone. And we end up with p squared minus 3p minus 4 is equal to 0. Okay, time to use the zero product rule. It doesn't help me when it's all adding and subtracting, but if I can get it to multiplying, then I'm in business. And this does factor. This can go p minus 4, so that's a factor. It is multiplied by this other factor. P plus 1 is equal to 0. So the zero product rule is going to help us out here. Just pointing out this, just that, without the equal sign and the 0, that's an expression. But if I take the whole thing, okay, that's an equation. And I can use the zero product rule to help me find the answer. The only possibility is maybe p minus 4 is equal to 0. Okay, so then p is equal to 4. Or maybe p plus 1 is equal to 0. Maybe p is equal to negative 1. So these are our solutions. These are our roots, you might say, for that equation. All right, the next one. Let's try this one out. Again, some fractions, but that's no big deal. I'm going to change things around here a little bit. This 2 minus x kind of bothers me. And I'm going to actually say that, you know, if you think about it, a 2 minus x and an x minus 2, they're just off by a minus sign. So how about we rewrite this? And we go, all right, 1 plus, we'll do a little factoring while we're at it, 12 sitting on top of x minus 2, x plus 2 equals, now I'm going to write this as not a negative 3, but I'm going to change this to a plus 3. So I'm changing it by a minus sign, multiplying by a negative 1, and that's okay if I multiply this by a negative 1 as well, which is actually going to turn into a nice x minus 2. So we had those reversed factors again. That 2 minus x is reversed compared to x minus 2. Now that x minus 2 matches the other x minus 2. It's going to make finding a least common denominator a lot more tolerable. I don't have to have 3 binomials in there, just a couple. Right? The least common denominator here would be x minus 2, x plus 2. Okay, let's give every term a kick with the least common denominator. That term, and that term. They all get kicked by it. That's going to turn into this. The 1 gets a kick with that LCD. The next term also gets a kick with the LCD, but it's just going to reduce everything. It'll just look like a 12. And then over here, the 3 gets kicked with that LCD. I'm glad I found that reverse factor. It makes things a little nicer here. The x minus 2's reduce, but the 3 will still get kicked with an x plus 2. Okay, let's keep tidying up. Looks like we're going to have an x squared minus a 4 plus a 12 is equal to 3x plus 6. It's quadratic. We might as well shove everything onto one side. I'm going to go left. So we're going to have x squared minus 3x plus 2 is equal to 0. Okay, zero product rule. It doesn't help me when there are minuses and pluses in here. I can't really see the answer. But if I can factor this thing and get it to say x minus 1 times x minus 2 is equal to 0, I now have two things multiplied together to make 0. It's got to be one or the other. So I can say, all right, here are my answers. My solutions, my roots are 1 or negative 2. But wait, hang on. Negative 2. Negative 2 is not a good plan because it doesn't work up here. It actually causes division by 0, right? This x plus 2 would turn into a big problem. Sorry, I said that backwards. Let's back up here a little bit. Not a negative, a plus 2. This plus 2 is still a problem. It's going to cause a problem with the x minus 2 terms. It's going to cause a division by 0. So we have to throw that one away. Right? So I'm just going to put a little note in here. Wait. And again, sorry for that mistake a second ago. X is equal to 2 is no good. Kind of picked up an extra answer in there. We picked up an extra root, and it has to be thrown away. So really the answer is just x is equal to 1. It's possible to pick up those extra answers, extraneous roots, people call them, whenever you're working with fractional equations and you multiply by an LCD. That multiplying by the LCD kind of hides the problem for a little while. All right, final page. And a little more equation solving here. This one, whoa, it's looking intense. And I'm a little scared right away, right? The first thing I'm noticing is this thing has x's and y's, right? Like, how can you have them both, right, in the same equation? Well, that's fine. We'll just see if we can use the zero product rule and try to clean this thing up. And speaking of cleaning it up, why don't we go and just do a little simplifying first? So I'm happy with that 12/5 x squared y, but over here let's distribute. So distributing, we're going to have a 2y on top of a 3, and then minus. Okay, a little reducing here. We're going to have a y hitting the 9x and all like on top of the 15. You can write it like this, 9xy all on top of 15 if you want. Or you could have reduced it a bit. It's not going to make much difference. Either way, you have a 3 and a 5 here. So for this story, the least common denominator is definitely a 15. We're going to need to take a 15 and kick every single term in this story. And when we do, this is what happens. We're going to end up with 12 x squared y. The 5 will reduce with the 15, but a 3 will also show up. It kind of survives. All right, let's keep going through the equal sign. We're going to have a 2y. Now when the 15 comes in, it will reduce the 3, but there will still be a 5 hanging around. That's okay. It's making things bigger, but at least there are no fractions. And then the 15 entirely cleans out the 15 that's down here. So we'll have just a minus 9xy. Ooh, looking messy. More tidying. 36 x squared y would equal 10y minus 9xy. Now, again, you might be looking at it going, what are you supposed to do with that? How does this even make sense when there are x's and y's? It's okay. Just aim for the zero product rule, right? That's going to be our plan. But it needs to be exactly that. It needs to be a zero product. So we have to make a whole bunch of stuff multiplied together equaling 0. I suggest we shuffle everything to one side. Let's go over to the left. So we can say you've got 36 x squared y. I'm going to write this as plus 9xy. I'm just going to put that one next. Subtract 10y is equal to 0. I'm just sort of running out of some room, so I'm going to skip a step here and do that. And you'll see why I did that right here. What can we pull out of this? What's common to all of this? And the answer is a y. And when I pull the y out, I have this beautiful little quadratic left over. 30, well, you might not say beautiful because it's got a leading coefficient that isn't a 1. Well, a lot of them are like that. 36 x squared plus 9x minus 10 is equal to 0. We're getting close, right? I've got a product, and it's equal to 0, but I can even do better. I can do some factoring again. This trinomial factors, that's why I wanted to put the 9 term before the 10, because it has the x's instead of just the constants. This does factor to 3x plus 2 and 12x minus 5. Okay, it is a product. 3 things are getting multiplied together, and it is equal to 0. So we can tell people what the answers are. Here are ways that you can get that expression to work. Any way you can make those factors equal to 0 will do. So here are some possibilities. X could be, for this factor, a negative 2/3. That would make it equal to 0. Or x could be 5/12. That would make that other factor there equal to 0. Or, here's another solution, this y out here. If the y was equal to 0, that would work too. That would wipe everything out. Now we did multiply by a least common denominator, so you should check to make sure none of those cause division by 0 in the original question. They don't, so they're all good. Any one of those three things, x being negative 2/3, x being 5/12, or y being 0, would actually get things to be nice. Number 9, sometimes we're going to solve equations graphically, right? That's going to be a technique we'll use for algebra that's just kind of a little bit over our heads, like maybe this one here. We have a polynomial and then an exponential. I think those are called transcendental equations, and you're stuck algebraically. There's no nice way for us to do that. But what you could do is this technique. Why don't we go and just take our graphing calculator, and we're going to graph the left-hand side, right? That's this part here. And we're going to say, hey, why don't we at the same time graph the right-hand side? Put them both on the same graph. So I'm just going to go to my graphing calculator. I'm going to put both of those in simultaneously. So I have a negative 2x squared minus a 3x plus a 4. That'll be one graph. And then 2 to the x minus a 3. And I'm going to graph them both at the same time. I like zoom number 4. Just kind of draws a nice picture where the tracing works well. Okay, so there it is, just like you've got in your notebook there. There are these places where the two graphs actually intersect, right? So yeah, I've graphed the left-hand side, that's this one, and I went and graphed the right-hand side, that was that one there. And I want to know when they're equal. When does the left-hand side equal the right-hand side? Well, there is a solution, and there is a solution. We need to find those x values. Where is it on the x-axis that those solutions happen? Well, no problem. My calculator is pretty good at this. I can say, hey, calculate an intersection, number 5. And it says, can I use curve number 1 as one of the curves? Yep. Can I use curve number 2 as another? Yep, sure. Got a good guess? I don't know, like this one, somewhere around minus 3. And it says, well, it's not minus 3. It's actually, looking at it there, it's a little hard to read there. I'm just going to quit and see if it's hiding in my x's right now. Yeah, there it is, negative 2.7470. That's one of them. It's not the only answer, but it's one of them. Now, for AP Calculus, if you're writing down a number that is not a terminating decimal and you want to round it, you must go to 4 decimal places. So I have to write this as 7470. I don't even have to worry about rounding the 4th decimal if I go to 4, but I have to go to 4. You can't go to 2 decimals. It's not a sig fig thing. It has to be 4 decimal places, then stop. And it is totally fine to not even worry about the rounding once you've gone to 4. Okay, so that's one of the answers. Let's go back to that graph and see if we can find the other one. So we're going to go second calculate, number 5, first curve, yep, second curve, yep, and I don't know, it's somewhere near, out here, I don't know, near 1. And it goes, oh yeah, it actually is 1. So I'm looking at this x value, right? X is equal to 1. Beautifully perfect 1. I don't have to write that one to 4 decimal places because it's exactly 1. But if I'm rounding, I have to go to at least 4. Okay, last little thing, just about things being equal to 0 or things being undefined. Let's say I have this expression, this function, which is equal to this trinomial divided by the other one. I can factor this. This one factors x plus 3, all on top of x minus 4. And the bottom factors as x plus 1, all on top of x minus 8. If somebody's asking you, hey, that fraction, when is it equal to 0? Right? That's what this first box is asking. How do you make a fraction equal to 0? Well, the only way you can do it is if the top is equal to 0. Okay, the numerator, of course. I just like saying the top. It's easier to write. So you look at it and go, what would it take to make the top of this fraction equal to 0? Well, it's kind of like the zero product rule happening here. If you want that to equal 0, then either x is equal to negative 3 or x is equal to 4. That would do it. if you want to make this fraction have no meaning, if you want to make it so big that it's bigger than any number we can imagine, and that's what we mean when we say it's undefined, the only way we can pull that off for the fraction is to make the denominator, to make the bottom equal to 0. So if I wanted to worry about this fraction being undefined, yeah, that'll happen when x is equal to -1 or when x is equal to 8. And that finishes up our day, just looking at a little review of working with expressions and working with equations.